Hi everyone. As always, for these problem set videos, if you go down to the description, you can find the times, so you can just click on the specific questions that you want to watch. You can also find a copy of this problem set, as well as the answers to this problem set. So if you want to use those things, please go ahead. So since I've done several of these before, I'm just going to go ahead and get started. So in this video, there's going to be a lot of times where we draw Lewis structures, and when I draw the Lewis structures, I'm going to just draw them. I'm not actually going to show how I drew them. If you'd like to review how to draw Lewis structures, that's covered in great detail in the previous problem set for chapters 7 and 8. So the first question says, give the approximate bond angle for a molecule with the shapes linear, trigonal planar, and tetrahedral. So I'm going to bring up our sheet here that tells us about these different things. So we have linear, trigonal planar, and tetrahedral. For a linear molecule, the bond angle is 180 degrees. For the trigonal planar molecule, the bond angle is 120 degrees. And for a tetrahedral molecule, it's 109.5 degrees. Here they put it as 109 degrees, but it's actually 109.5. You'll notice in the choices there is no 109. So here it's choice letter A. Linear, 180. Trigonal planar, 120. Tetrahedral, 109.5. Unfortunately, that's something you simply have to memorize. Question number 2 says, what is the electron geometry and molecular geometry of carbonate, CO3₂-? So as promised, I'm just going to draw the Lewis structure, okay, which I do using the same rules that I go over in great detail in the previous problem set and in the video. So if you're not sure how to draw Lewis structures, you have to start by drawing the Lewis structure. And this is the Lewis structure of carbonate. Now what I want to do is I want to count domains. So what counts as a domain? An atom and a lone pair counts as a domain. So I have 1, 2, 3 domains. And I also want to see how many of those domains are lone pairs. Well, with respect to carbon, the central atom, there are no lone pairs on carbon. So there's 3 domains and 0 lone pairs. Now I can bring up the same sheet that I used in the previous question here. So the first thing we do is we go to 3 domains. The electron geometry always comes out of this first column. In this case, for 3 domains, it is trigonal planar. However, since this molecule has no lone pairs, okay, it's 3 domains, 0 lone pairs. So the molecular geometry is also trigonal planar. If there were a lone pair, then it could be bent or angular, but there's not, so it's trigonal planar. So here, both the electron geometry and the molecular geometry are trigonal planar, which is choice letter E. The next question is more of the same. It asks for the electron geometry and molecular geometry of SiF4. So we want to go ahead and draw SiF4, draw the Lewis structure. Again, I go over that in great detail in the previous problem set, so I'm not going to cover that here. I'm just going to directly draw the Lewis structure. So once I've drawn the Lewis structure, then I can find the electron geometry and the molecular geometry. Well, in this case, I have 1, 2, 3, 4 domains with respect to silicon. Remember, what counts as a domain is atoms, in this case the 4 fluorines, and lone pairs. There are no lone pairs on Si, so there's 4 domains and 0 lone pairs. So this is what I care about. How many domains are there? How many of those domains are lone pairs? When I use my table, if I find 4 domains, okay, the electron geometry is tetrahedral. Because none of the domains are lone pairs, the molecular geometry is also tetrahedral. So in this case, that is choice letter A. This last question, like this, asks us, determine the electron geometry and the molecular geometry of NCl3. So we again have to draw the Lewis structure, which again is covered in the previous videos. So if you need more practice with that, please refer to the previous problem set where we cover that. But this is the Lewis structure of NCl3. we again want to count the domains. What counts as domains? Atoms and lone pairs. So we have 3 chlorines plus the lone pair. So we have a total of 4 domains, one of which is a lone pair. So we have 4 domains, 1 lone pair. Let's use the chart. So, I'm trying to get this all on the screen here as best I can. So, 4 domains. The electron geometry is tetrahedral. We don't consider the electron geometry. For the electron geometry, we don't consider the lone pairs. So the electron geometry is tetrahedral because it has 4 domains. There's 1 lone pair. So see, this is a chart. So we go to 4 domains, 1 lone pair, and we find that it's trigonal pyramid. They write that as trigonal pyramidal. So the electron geometry is tetrahedral. The electron geometry always comes out of this column. It says electron pair geometries. They're the same if there's no lone pairs, molecular geometry and the electron geometry. In this case, there's 4 domains, so it's tetrahedral, but there is 1 lone pair. So we go over to 1 lone pair, and we get trigonal pyramidal as the molecular geometry. This question says, consider the molecule below. Determine the molecular geometry at each of the 2 labeled carbon atoms. So essentially what we need to do is count the domains. Now, in this carbon 2, it's not clear, but CH3 looks like this. I can't really draw it over that. So this carbon is bonded to 3 hydrogens and a carbon. But let's do carbon 1 first. Carbon 1 has 1, 2, 3 domains and 0 lone pairs. So 1 is 3 domains and 0 lone pairs. So we use our chart, 3 domains, 0 lone pairs. Carbon 1 is trigonal planar. Carbon 2 is 4 domains, 1, 2, 3 hydrogens, and the carbon. So carbon 2 is 4 domains. And again, this carbon doesn't have any lone pairs, so it's 0 lone pairs. So the first one was trigonal planar, 3 domains and no lone pairs. The second one is 4 domains and no lone pairs, which is tetrahedral. So if we look here, trigonal planar for the first one, tetrahedral for the second one. That is choice letter C. Question 6 says, how many of the following molecules are polar? Well, in order to determine if they're polar or nonpolar, we need the Lewis structure. Again, as I mentioned several times, if you watch previous questions in these videos, the Lewis structures are covered in problem set 7 and 8. Problem set 7 and 8. So they're in chapter 7 and 8. If you need to review the Lewis structures, please go back. So I'm just going to draw the Lewis structures of these things. So we have Br, which has 2 lone pairs and 3 Cl's attached like this. This is the Lewis structure of BrCl3. So I'm going to draw all the Lewis structures and then we'll come back and determine if they're polar or nonpolar. CS2 is C double bond S, just like CO2, except you have sulfurs, which are 1 below it on the periodic table. That's why it's the same. SiF4, so we have Si bonded to 4 Fs, like so. And then finally SO3, which has 3 double bonds to oxygen, like so. So now we have the Lewis structures. Now, how do we determine if molecules are polar or nonpolar? Sorry, I didn't realize I was off the screen here. So now we need to determine if the molecules are polar or nonpolar. So I simply drew the Lewis structures of all 4 of these things. It's a long question because you have to draw 4 Lewis structures. All right, so if all the domains are the same, then it's nonpolar. So if we look here, what counts as a domain? Let's remember, it's lone pairs and atoms. We have 2 lone pairs and 3 atoms. They're not all the same. This one is polar. How about this one? Carbon has a sulfur on this side and a sulfur on this side. Nothing else. Both domains are the same. This one is nonpolar. Although the carbon-sulfur bond is slightly polar, it's overall nonpolar because you have 1 sulfur on this side and 1 sulfur on this side. So there's no net pull of electron density. Same thing here. We have SiF4. The SiF bond is extremely polar, but they're all in opposite directions. Even in three-dimensional space, where it's a tetrahedron, they're still in opposite directions. So we have 4 fluorines. All the domains are fluorine. They're all the same. So it's non-polar. And then same thing here. We have 3 oxygen domains. All 3 oxygen domains are the same. So this one is also non-polar. So to answer the question, how many of the following are polar? Well, there's just one. BrCl3. One polar molecule. Question number 7 is very similar to question number 6. We need to start by drawing the Lewis structures. So here we have PCl5. And all this, I'm starting by drawing the Lewis structures, which again are reviewed in the previous problem set. So if you need extra help with the Lewis structures, please review that before you do this, because the first step here is to draw the Lewis structures. So if we look at PCl5, all the domains are chlorine, all the domains are the same, so the electronegativity differences cancel each other out, and this one is non-polar. If we look at COS, we have carbon on one side, carbon in the middle, oxygen on one side, and sulfur on the other. Here, the domains are not the same. One's oxygen and one's sulfur. So there's going to be a net pull of electron density towards the oxygen, and this one is polar. All right, so we're looking to see if all the domains are the same. In this case, all the domains are chlorine. In this case, one's oxygen, one is sulfur. I should note that domains are lone pairs and atoms. That's how we count domains. XeO3. We have Xe, and we have it bonded, double bonded to 3 oxygens, like so. And when we look at this, we have 3 oxygen domains and 1 lone pair domain. The domains are not all the same. 3 are oxygen, 1 is a lone pair. That makes this polar. SeBr2, we have Se, it's got 2 lone pairs, and it's bonded to 2 Brs, like so. Again, all the domains are not the same. 2 of the domains are lone pairs, 2 of the domains are bromine. This is overall polar. So to answer this question, how many of the following molecules are polar? After we drew all the Lewis structures, we found out that 3 of the following molecules are polar. So I think it goes without saying for these 2 questions, first draw the Lewis structure, then figure out if it's polar or non-polar. You can't figure it out just by looking at this. Sometimes you can. I'm not going to go through how to do that, but it's not simple. It's much easier to draw the Lewis structure, then see if all the domains are the same. Question 8 says, give the hybridization for Br and BrCl3. Well, you got to start with the Lewis structure. Again, lots of Lewis structures in the beginning part of this problem set. So we're going to start with the Lewis structure of BrCl3. I actually drew this already in a previous problem, number 6. So I'm just going to draw it for you again here, like this. Now, what we need to remember is that the same things that are in domains are in hybrid orbitals. Technically, it's sigma bonds and lone pairs, but you can count it the same way that you count domains. There are 1, 2, 3, 4, 5 domains, 2 lone pairs, and 3 atoms. So here we have 5 domains. If we have 5 domains, we have to have 5 hybrid orbitals. Well, what are our choices? We have it as 3 P's, 5 D's. You'll never use 5 D's, but there are 5 D's. And we need 5 domains. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We need 5 orbitals to hybridize because we have 5 domains with electron density in them. So therefore, we have sp3d. We just abbreviate this sp3 because there's 3 P's and then the 1d. So this is our 5 domains, sp3d. And I'll do a couple more questions on this as we continue along. So it says, how many of the following molecules have sp2 hybridization in the central atom? So don't forget, our possible orbitals for hybridization are an s, 3 P's, and 5 D's. You'll never use 5 D's. The biggest one you get in Gen Chem is sp3d2 with 2 D's. but these are the possible orbitals, right? There's 1s, there's 3p's, and there's 5d's. So let's write it out. Let's draw HCN. Needless to say, the first thing you need to do here is to draw the Lewis structure. So HCN, a nasty molecule, hydrogen cyanide. Now let's look at the central atom. How many domains does it have? It has 2 domains. The hydrogen and the nitrogen, so 2 domains. If it's got 2 domains, it needs 2 orbitals to hybridize, because those electrons in those domains are going to be in hybrid orbitals. So this one is sp hybridized. It's not sp2. SO2. SO2 looks like this. So notice we always have to draw the Lewis structure first. SO2 looks like this. How many domains do we have? We have 2 oxygens and a lone pair. Remember, atoms and lone pairs are domains. So we have 1, 2, 3 domains. Well, if we have 3 domains, we need 3 orbitals. spp, all right, these 3, which is sp2. So there's one of them that's sp2 hybridized, because that's what it asks us. OCl2. OCl2 looks like this. How many domains do we have? 1, 2 chlorines and 1, 2 lone pairs. So 1, 2, 3, 4 total domains. Well, if we have 4 domains, we need 4 hybrid orbitals. 1, 2, 3, 4. SPPP, which we abbreviate sp3. Finally, XeCl2. Xe actually has 3 lone pairs here in XeCl2. No, it's a noble gas compound, so it's a little bit weird, but it is what it is. We're going to draw it out anyway. How many domains we have? Well, atoms and lone pairs. 1, 2, 3, 4, 5. 5 domains. That means we need 5 hybrid orbitals. At 1, 2, 3, 4, 5. SPPP, D. We abbreviate that. SP3D. So, how many of these are sp2 hybridized? It looks to me like we have 1 sp2 hybridized central atom. Number 10 says, use molecular orbital diagram below to determine which of the following is the most stable. Well, if we want the most stable, we want the highest bond order. All right, and bond order is equal to bonding electrons minus anti-bonding electrons divided by 2. So this is how we're going to find the bond order. So these are the atomic orbitals, and then when we combine these two things together, we get molecular orbitals. So 2 atomic orbitals form 2 molecular orbitals, constructive interference and destructive interference, bonding and anti-bonding. How do you recognize the anti-bonding? The star. So we have 1, 2, 3, 4 bonding orbitals, and with the star, 1, 2, 3, 4 anti-bonding orbitals. So 4 regions of constructive interference, bonding, and 4 regions of destructive interference, anti-bonding. So how do we know how many electrons to put in here? Well, we put in the valence electrons. So if we look at fluorine, fluorine has 14 valence electrons. Right? There's 2 fluorines, each has 7 valence electrons, for a total of 14 valence electrons. If we look at O2 2+, well, each oxygen has 6, 2 6s is 12, but it's 2+, so it has 10 electrons. Turns out that's the magic number, and I'll show you why in a minute. F2, 2-, well, F2 has 14, if it's 2-, it has 16 electrons. F2 2+, well, F2 is 14, if it's 2+, it has 12 valence electrons, and Ne2 2+, Ne has 8 each, so 2 of them is 16, but it's 2+, so it again has 14 electrons. So I mentioned a second ago that 10 is the magic number, and here's why. When you have these larger atoms, like oxygen, fluorine, and neon, larger as compared to nitrogen and carbon and boron, they use a slightly different table, then basically 10 is the magic number. And the reason for this is, let's put these 10 electrons in. So we put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. we have as many electrons as possible in bonding orbitals. If we have any less electrons, we have less in bonding orbitals. If we have any more electrons, they go into anti-bonding orbitals. If you recall, the bond order is the bonding electrons minus the anti-bonding electrons. So we want as many in bonding orbitals and as few in anti-bonding orbitals. Let's actually do this. So the bond order is equal to the bonding electrons, the ones without the stars, the ones that go down. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electrons in bonding orbitals. How many electrons are there in anti-bonding orbitals? Just 2. So it's 8 minus 2 divided by 2. And the bond order, I didn't really need to put the electron symbol there. The bond order here is 3. And if you practice this a little bit, you'll realize 3 is the highest that you can get. This makes O2, 2+, the most stable of these choices. So in this question, we're shifting gears to the gas law. Question 11. It says, what pressure in atmospheres will 0.44 moles of CO2 exert in a 2.6 liter container at 25 degrees C? So the ideal gas law is PV equals nRT, where P is the pressure in atmospheres. Sometimes it's given in torr or millimeters of mercury, and it's important to know that 760 torr or 760 millimeters of mercury equals 1 atmosphere. V is the volume, and it has to be in liters. N is moles, that's a unit, so it's in moles. R is the ideal gas law constant, 0.08206, and that's liter atmospheres per mole K. And then finally, the temperature is in Kelvin. And it's important to remember that the temperatures are sometimes given in Celsius. So Kelvin equals Celsius plus 273. Sometimes 273.15. It doesn't really matter on a multiple choice type deal because the answers aren't going to differ enough. They're not going to be close enough that the 0.15 is going to make any difference, so I just leave it off. Often temperatures are only read to no decimal places anyway. Anyway, that's not super important. So this is the ideal gas law, PV equals nRT. So let's look at this as applied to question number 11. I will note that this will be applied to several other questions, and I'm not going to go through it in detail every single time. All right, so let's take a look here. PV equals nRT. Well, in this case, it says, what pressure will 0.44 moles of CO2 exert in a 2.6 liter container at 25 degrees C? So we want to solve for P. So we're going to divide both sides by V, divide by V. And we find that P, pressure, equals nRT over V. Well, let's look. Moles, we're good. Liters, we're good. 25 degrees C, we're not good. So we have to add to that 273, and we get 298 K. We have to plug the temperature in Kelvin for the ideal gas law. So now let's plug in. N is our 0.44 moles times R, which is our constant, 0.08206. I'm not going to write the unit every time because it gets messy in these little spaces. All right, so just 0.08206. That's liter atmospheres per mole K. Times the temperature, which is 298 K, divided by, I meant to make that a straight line, and it didn't go well. All right, our volume in liters, which is 2.6 liters. When we do all that math, we find that this gas has a pressure of 4.1 atmospheres, which is choice letter D. Question 12 says, what temperature must a balloon initially at 25 degrees C and 2 liters be heated in order to have a volume of 6 liters? So in this case, we're only relating the temperature and the volume. It turns out that Charles' law relates the temperature and the volume. Another way of remembering this is the temperature and the volume are on opposite sides, so that means they're directly proportional. As the temperature of a gas goes up, the volume of a gas goes up. If you think about a balloon, if you heat up a balloon, it gets bigger. So this is basically what we want to remember. So in this case, the number of moles is not changing, okay? And the pressure on, external to the gas is also not changing. So what is changing? Temperature and volume. Well, we can remember that V1 over T1 equals V2 over T2. And this is always the case for variables on the opposite side. So volume is on this side of the ideal gas law, and temperature is on this side of the ideal gas law. So they're directly proportional. This is how you write a direct proportionality, which you're probably familiar with. The only thing that we need to remember is the temperature has to be in Kelvin. So we can't put in 225C. We have to add 273 to that and put it in as 298 K. All right, so what's our initial volume? Our initial volume is 2 liters. Our initial temperature is 298 K. Our final volume is 6 liters. And our final temperature, well, that's what we don't know. So we're going to put that in as T2. To do this, you take 2 times T2, you cross multiply, and 6 times 298. And then after you multiply 6 by 298, you divide by 2. And what you find is that T2, I don't know why I put equals there, T2 equals 894 K. Another way of thinking about this is we tripled the volume, right, from 2 liters to 6 liters. So we have to triple the temperature from 298 to 894 K. So it's a big difference in temperature. That is choice letter C. Number 13 says, what pressure will 14 grams of CO exert in a 3.5 liter container at 75 degrees C? Well, we have PV equals nRT again. We're trying to solve for P. So pressure equals nRT over V. But there's a problem. We're not given moles, so we need to find moles. So if we take the 14.0 grams of CO times 1 mole of CO per 28.01 grams of CO from the periodic table, carbon plus oxygen is 28.01 grams, and we do that math, we find that there are 0.500 moles of CO. Well, now we can plug in. So N is 0.500 moles times R is a constant, 0.08206. It's the liter atmospheres per mole K. I don't have space to write it every time. Temperature, well, we can't plug in 75. We have to add 273 to that. So we get 348 K. So 348 K here. And the volume of this gas is given in the problem as 3.5 liters. When we do the math, we find that the pressure of this gas is equal to 4.1 atmospheres. And that is choice letter B. Question number 14 says, which of the following samples will have the greatest volume at STP? Well, one thing we need to remember is that 1 mole of any gas equals 22.4 liters at STP. And this is the so-called molar volume. So this is the volume of 1 mole of gas at standard temperature and pressure. The standard temperature is 273 K or 0 degrees C, and the standard pressure is 1 atmosphere. But it's 1 mole of any gas. We're given 22 grams of each gas. Well, which one are we going to have the most moles of? The one that's the lightest. Since helium has the lowest molar mass, 22 grams of helium is going to be more moles of helium than any of the other ones. Since we have more moles of helium, we'll have more volume of helium because the amount of volume that something takes up is dependent on how many moles are present, and there'll be more moles of helium present. Question 15 says, a 0.334 gram sample of an unknown halogen occupies 109 milliliters at 398 K and 1.41 atmospheres. What is the identity of the halogen? Well, how we're going to identify the halogen, believe it or not, is by its molar mass, which is a little bit counterintuitive. This seems like kind of a weird question. And normally, if you want to know the molar mass of something, you look it up on a periodic table. But in this case, we're going to use some experimental evidence, namely the mass, the volume, the temperature, and the pressure, to figure out the molar mass. So molar mass, experimentally, is grams over moles. Not surprising. Well, grams were given. We know that this is 0.334 grams. Moles we don't know, but what we do know is PV equals nRT. If I divide both sides by RT, N equals PV over RT. So I can find moles using the ideal gas law. How do I do that? Well, I need to plug in the pressure. It's given in atmospheres, so I'm good. 1.41 atmospheres. The volume is given in milliliters, so I need to divide by 1,000, 0.109 liters, so 0.109 liters. R is a constant, 0.08206, that's liter atmospheres per mole K. And the temperature is given in Kelvin, so 398 K. When I do that math, I find out that there's 0.00471 moles. Well, now I have both my variables. I have my grams and I have my moles, so I can find molar mass. So 0.334 grams divided by 0.00471 moles. And when I do all that math, I find that it's 71.0 grams per mole, which is pretty darn close to the molar mass of chlorine. It's 35.45, so you get 70.9, which is very close to 71. So this is quite an involved, complex problem, but it is a good application of the gas law. Question 16 says, a mixture of 0.22 moles of CO, 0.35 moles of hydrogen, and 0.64 moles of helium has a total pressure of 2.95 atmospheres. What is the pressure of hydrogen? Well, this is using Dalton's law of partial pressures. And Dalton's law of partial pressures says that the pressure of hydrogen is equal to the mole fraction of hydrogen times the pressure total. Before I go into it for this particular example, how to calculate all this stuff, let's just think about it as a more simplified example. Air. Air is roughly 78% nitrogen and 22% oxygen. That's not perfect, but it's close. Okay, and air right now is exerting about 1 atmosphere of pressure. So your body, skin, or whatever, is experiencing 1 atmosphere of pressure right now. Well, what causes that pressure? It's caused by air molecules bouncing into you. Well, if 78% of the moles of gas in air are nitrogen, then 78% of the pressure is nitrogen bouncing into you. And 22% of the pressure is oxygen bouncing into you. That's all Dalton's law of partial pressures is. It's that individually, the percentage, or the fraction, which is a percentage, the same as a percentage, except you don't multiply by 100, is the amount of the pressure that's exerted. So 78% of the air is nitrogen, 0.78 atmospheres are the pressure of nitrogen. 0.22% of the air is oxygen, 0.22 atmospheres of the pressure are caused by oxygen bouncing into you. All right, now that we have some idea of what Dalton's law of partial pressures is, and I understand that was like a 30-second explanation, let's figure out how to calculate these things. Mole fraction is the same as a percentage, except we don't multiply by 100. So the mole fraction of hydrogen is equal to the moles of hydrogen divided by the total moles. So in this case, the moles of hydrogen is 0.350 moles of hydrogen, and the total moles is 0.220 moles plus 0.350 moles plus 0.640 moles. So all the moles, the CO, the hydrogen, and the helium. When you do that, you find that the mole fraction of hydrogen is 0.289. Now, if this was a percentage, we would say the mixture is 28.9% hydrogen. But mole fraction is the same. A fraction, or any fraction, is the same as a percentage, except you don't multiply by 100. Now to find the pressure of hydrogen. The pressure of hydrogen is 0.289, because it's 28.9% hydrogen, times the total pressure, 2.95 atmospheres. And when you do that math, you find that the pressure of hydrogen is 0.853 atmospheres. So simply stated, the gas is 28.9% hydrogen, so 28.9% of the pressure comes from hydrogen bouncing into the walls of the container. Number 17 says, determine the volume of O2 at STP formed when 50 grams of KClO3 decomposes according to the following reaction. And the molar mass for KClO3 is given. So at STP, 1 mole of, in this case, oxygen or any gas equals 22.4 liters of, in this case, oxygen. So this is a stoichiometry gas law equation combined. So what we're going to do is we're going to convert from the grams of KClO3 to moles of KClO3 using the molar mass. Then we're going to convert to moles of oxygen using the balanced chemical equation. And then, using this equality right here, we can find the liters of oxygen, or the volume of oxygen if you want, that is formed. So let's start with our 50.0 grams of KClO3 times, we put the molar mass on the bottom, which is given to us, 122.55 grams of KClO3 on the bottom, 1 mole of KClO3 on the top, times, using the balanced chemical equation, we want to convert from moles of one thing to moles of another. So we have 2 moles of KClO3 on the bottom and 3 moles of oxygen on the top, times, well, we know that every mole of oxygen or any other gas is 22.4 liters at STP. We want moles of oxygen to cancel out, so we put the 1 mole of O2 on the bottom and the 22.4 liters of O2 on the top. Do all the math, multiply by the top, divide by the bottom, repeat until you get to the end, and you get 13.7 liters of oxygen. So the answer to this question is choice letter D, 13.7 liters. So this is a combination of the gas law and stoichiometry. Number 18 says, below there are several curves of nitrogen at several temperatures. Which curve is N2 the highest temperature measured? Well, anytime you're asked to interpret a graph, the first thing you need to do is read the axes. So the first axis on the x is molecular speed. And the second axis on the y is relative number of particles. Now, it doesn't you don't have to read this one first, it doesn't matter. But we have speed down here, and we have a relative number of particles. So if you look at the tops of each of these curves, you get the median speed. So if we look at D, the median speed is somewhere around 250 meters per second, I assume. It's not given as units, which is weird, but I would assume it's meters per second. And if we look at A, it's somewhere around 1200 or a little bit less, 1150 meters per second. So this is clearly the median speed of A is much faster than the median speed of D. So it asks us, which of the following is measured at the highest temperature? Well, at higher temperatures, molecules are moving faster. So A is the highest temperature. There's another thing to note here. You don't actually need to notice this to solve this problem. You'll also notice that as you heat A up, that A has a much greater range of speeds. So D has a more confined or a narrower range of speeds, and A has a broader range of speeds, which is another effect. One other thing I should mention here. In this question, we're asked about temperature, but in another question, you might be asked about molar mass. If you take molecules with different molar masses at the same temperature, bigger molecules will be moving slower. Smaller molecules will be moving faster. This is how helium, the same amount of helium at the same temperature, the same number of moles, can exert the same amount of pressure as xenon, a much larger gas. Well, xenon would be moving much slower on average, okay, and helium would be moving much faster. So you can interpret this graph that way too. It doesn't ask us to. This gives us at different temperatures, but it could also be done in terms of different molar masses. It says, which of the following are variables in Boyle's law? I think you just have to memorize this one. P1 V1 equals P2 V2. This is Boyle's law. It relates pressure and volume. Okay, so what happens to the pressure when you change the volume? This is like you put your thumb at the end of a syringe and you push the plunger down, the pressure on the syringe goes up. Obviously, you don't want to have a needle in it when you do that. Okay, so that's Boyle's law. If it asks you which variables were constant, well, the amount of gas, in our case in the syringe, would be the same. So N is constant, and the other thing is the temperature doesn't change. But in this case, it asks which of the following are variables, and the answer is pressure and volume, and I think that's just something that's one of these kind of memorized ones. Here's another question where we need to know the name of a gas law. Number 20 says, which of the following are variables in Charles' law? Well, Charles' law relates volume and temperature. It is V1 over T1 equals V2 over T2. And just like the previous question where you essentially have to memorize that, this is the case here. So in this case, it relates volume and temperature, which is choice letter B. I will note that the amount of gas in the container, when you're messing with its volume and or temperature, is going to be constant, so moles will be constant. The other thing is the volume, not the volume of the container, the external pressure on the container would also have to be constant. So these are the variables in Charles' law. All right, number 21 says, determine the density of NH3 at 435 K and 1 atmosphere. So density equals mass divided by volume. In this case, the mass has to be in grams and the volume has to be in liters. So we need to get grams of the gas and we need to get liters of the gas. And we're not given any information, so how are we going to do this? Well, since this is in the gas law chapter, my guess is you figured we're going to use the gas law, and you'd be correct. But we have to make an assumption here. Let's assume 1 mole of NH3. Why do we assume 1 mole? Because we know that it's 17.04 grams of NH3. So now one of our two variables is taken care of. 1 mole of NH3 is 17.04 grams. We just look it up on the periodic table. Nitrogen plus 3 hydrogens, and it gets us the 17.04 grams. Well, how can we find the volume of this? Gas law will help us. PV equals nRT. In this case, we want to solve for V, so we divide both sides by P. Volume equals nRT over pressure. We just said we're going to assume there's 1 mole, so N is 1. R is constant, 0.08206, that's liter atmospheres per mole K. The temperature is given, 435 K, divided by the pressure is given, 1 atmosphere. When we do that math, we find that the volume of this gas is 35.7 liters. We now have both variables. Plugging in 17.04 grams divided by 35.7 liters, and when you do that math, you get 0.477 grams per liter. And that is the density of ammonia at in these particular conditions, 435 K and 1 atmosphere. Oh, sorry, that is choice letter A. Question 22 says, a mixture of 1 mole of helium and 1 mole of neon are at STP in a rigid container. Which one of the following statements is true? So we have 2 moles of gas at STP. Remember that 1 mole equals 22.4 liters at STP. That'll come up in a second. It says both gases contribute equally to the density of the mixture under these conditions. That is not true, because helium is lighter than neon. So 1 mole of helium is going to weigh less even though it takes up the same volume. So each gas will take up the same volume at STP, or any gas will take up the same volume at STP. So the density contribution is not equal. That is not true. The mixture has a volume of 22.4 liters. No, we have 2 moles of gas. 1 mole of helium and 1 mole of neon. 2 total moles of gas. 1 mole is 22.4 liters. 2 moles, not 22.4 liters. Okay, it would be 44.8 liters, but that's not what it says. Both gases have the same average kinetic energy. At any given temperature, the 2 gases are going to have the same average kinetic energy. In fact, that's what temperature is. It's a measure of average kinetic energy. So any substance with the same temperature will have the same average kinetic energy. So that is a true answer. Both gases have the same molecular speed. No. In order for helium to exert the same pressure as neon, helium has to be moving far faster than neon. So therefore, helium molecules are moving on average faster than neon molecules. So this isn't true, and obviously not all of the above are true, because we found a bunch that weren't true. So that is the answer to question number 22. Question 23 says, which of the following statements are true? Particles of different masses have the same average speed at a given temperature. This is not true. Okay? At a given temperature, smaller molecules are moving faster than larger molecules. At very high pressure, a gas will occupy a larger volume than predicted by the ideal gas law. That is true, because at very high pressures, the size or the volume of the molecules plays a greater role. So therefore, the volume will actually be larger because we have to, at very high pressures, we have to actually consider the volume of the molecule itself. And the ideal gas law assumes that the molecules themselves take up no volume. And at intermediate pressures, that's pretty accurate assumption. But at very high pressures, that's not a great assumption. So that's the answer. The larger the molecule, the faster it will effuse. This is the opposite. Smaller molecules are on average moving faster, so they're going to effuse faster. That means go through a hole in a box faster. So we're going to knock that one out. For a given gas, the lower the temperature, the faster it will effuse. No, molecules effuse faster if they're moving faster. At lower temperatures, they will be moving slower. They will effuse slower. So that is not the correct answer. And obviously none of the above isn't the correct answer because we found one. So this is basically the answer to question number 23. Number 24 says, rank the following in order of decreasing rate of effusion. So decreasing means biggest first. So how do we determine rate of diffusion or effusion? It's the same. Okay, the molecules that are the smallest will be moving the fastest, so they will diffuse or effuse the fastest. So we need to look at the molar masses. If we look at these different molecules, the lightest one is helium. So helium will diffuse the fastest. Helium is greater than fluorine. Fluorine has a molar mass of about 38. Argon has a molar mass of about 40. So fluorine will diffuse faster than will argon. And then finally, SF6, I don't know the exact molar mass of SF6, but it's clearly bigger than F2 because there's 6 Fs instead of 2. So SF6 is going to effuse the slowest. If we look at this, helium, fluorine, argon, SF6, this is choice letter E on our list. All right, and we get to the last question. It says, which of the following statements are true about kinetic molecular theory? Kinetic molecular theory is essentially kinetic, motion, molecular, molecules. It's that gas molecules are moving around and bouncing off of each other. And we want to know which of the following is true. A single particle does not move in a straight line. No, the kinetic molecular theory says that molecules move in a straight line until they hit either the walls of a container or they hit another particle. So this is not true. The average kinetic energy of a particle is not proportional to its temperature. That's not true. Okay, the average kinetic energy is proportional to the temperature. If you heat it up, the molecules on average move faster. If you cool it down, the molecules on average move slower. So it is proportional to the average kinetic energy. The collision of particles with one another is completely elastic. That means that no energy is lost when the particles collide. This is a true statement about the kinetic molecular theory. It may not be a true statement about actual molecules in all situations, but for the kinetic molecular theory, this is an assumption. And then finally, the size of the particle is large compared to the volume, and this is not true. We consider that the size of the particle is essentially 0 as compared to the volume of the container. Said another way, in a gas, it's mostly empty space. So these are, this has been the final problem set, which covers chapters 9 and 10, and all the material in this course for General Chemistry 1.